Hello, my name is Christoph Ebert, and I'm very glad to be today at Vector Forum 2024 together with Luque of Tongji University. We are going to present this Vector Forum, which is about how to cope with autonomous vehicle and robots. We will get some very deep insight into current research and practice from Tongji University, Shanghai. And I suggest, Luque, that you briefly introduce yourself, then I will continue.
Thank you, Christoph. Hello, everyone. This is Luke. I work in Tongji University, and my research field includes embedded systems and autonomous driving systems. I'm very glad to be here to share something about the work we've done here. Thank you.
Thank you. And on my person, Christoph Ebert, I'm responsible for the consulting activities in Vector, and I will now share a few slides to give you an intro, and then we pass over to Luque. So, a few words on Vector. We are active in critical systems, primarily automotive, safety critical, mission critical, about 4,000 and a few hundred people worldwide. And we have different fields in which we work: lifecycle management, embedded software, where we are market leader in AUTOSAR, and testing, which also relates to today's field, testing of AI systems, for instance, AI-based testings, diagnostics, calibration, and consulting, which is my own responsibility. Vector Forum had been established some almost 20 years ago with the mission to connect your needs as our partners with our solutions. And we have addressed the 4 dimensions of our consulting activities, namely trust, technology, transformation, and training, with this Vector Forum over the years. This year, deploying emergent technologies, a key topic, because after the COVID slowdown, it's even more relevant now to address innovation and make sure that we get new technologies deployed into our different products, into our different solutions, into different markets. A few words on the forum itself. It's a 1-hour event. We do that every week. And the intro, which is currently running, is a few minutes, so don't worry. And then we have the presentation of about half an hour. And we will have room for Q&A. That is, I think, a very important part of the forum. Ever since the beginning, we don't want to make a static presentation. We want to have interaction. And it works typically very good. So you just can use a chat window and put questions here. And I will select then according to the topic and the ranking these questions so that Luc can reply to those. In case that you are on MS Teams with the browser, that could be sometimes technically difficult. So we recommend to use the app, and then you're on a safe side. In case that we have any sort of problem, because the whole thing is hosted by Microsoft, then we switch into WebEx, and that would be announced by an email. So have a look to your email. If we somehow lose you, maybe you find an email that we switched. We have so far never used it, which is good, because that's the whole idea of risk management. Those risks which you actively attack will not themselves actively attack you. That's the whole idea of risk management. Interaction makes, of course, sense, and that is why we have the chat window on the right side. Just put questions there. Or you can also like existing questions, which allows me later on to take those with the highest ranking. And finally, we will also have a quiz, which is ongoing, and you can just go to that link and then go to this quiz and put your answers. And we will announce the winners, which can be a seminar, training, books, etc., by the end of this Vector Forum in June. Aside that, generic guidance applies. I'm not going to explain everything. Of course, have your coffee, because for those of you in Asia, it's already late. For those in North America, it's quite early. For us in Europe, it's midday. None of these times is really good. So have a coffee, have a tea, enjoy that you really stay awake. The content will certainly keep you awake. And as so often with the risk management, also ensure that you know where to go in emergencies. Now, content-wise, we see in our annual review with our clients that both short and midterm challenges currently converge around a lack of competence and, in consequence, a slowdown in innovation. And these two topics were exactly the reason for this year topic, deploying emerging technologies. We want to help you to best use your competences, which are anyway scarce, to focus on the relevant new technologies, not to get too much lost in quality issues, technical debt, etc. This is what we can help you with as Vector Consulting Services. Beyond this presentation today, we had already 3 presentations which had addressed very different topics, from software-defined vehicle towards AI usage and development into cybersecurity. And we are going to continue next week into Healthineers, which is then a medical topic, and also then lessons learned from developing SDV infrastructure, and finally functional safety with the new respective challenges. It's every week 1 hour. Those of you who listen to this webinar as a recorded webinar, the only drawback which you have is you cannot interactively ask your questions, but you will certainly get the questions and answers from our current audience, and the audience I stimulate to raise your questions. All of that would be available in our YouTube channel, and of course you can still register for any further event at our homepage, which I will show you at the end. Today's presentation on autonomous driving technologies for robots and vehicles with Luc would be really addressing now the insights. And just a last topic before we go then ahead with the presentation of Luc is about giving you an introduction to this topic. And I want to start with a small survey, as we do every week. And the survey this time is a question again, yes, no. We already deploy novel AI-based testing methods. In other words, are you still on more traditional test schemes around coverage, automation, CX, or are you already moving into novel AI-based test schemes? Just yes, no. The survey is up and running. You should see that on your screen and or in this chat window. The challenge with all this autonomous system is, and that is also embedded into this question, that they perform beyond a single specification. We cannot specify all the behaviors, and that's the major difference to previous software systems where the algorithm would be specified with requirements and then implemented. Here we have something which in functional safety we call intended functionality. And intended means it's not specified. And if it is not specified, you cannot really go with coverage. You have to find new ways to identify corner cases, to identify the best way to harden these systems to make them robust. There's a rule of thumb that autonomous systems should be at least a factor 10 more reliable, more safe than human-operated systems, because that's the gap which we expect as humans, that technology is advanced, or otherwise we would not entrust our lives. A good example is airplanes. They fly autonomously. Many trains run in the meantime autonomously. That's because their functional safety is way better than what we could do as humans. With cars, we are not yet there, and therefore this is a continuous evolution path. And the solution is invest into verification validation techniques which help you into testing your AI systems. And of course, you can also get in touch with us to help you with that. All that being said, I hand over to my colleague, Dr. Lu Ke of Tongji University, and we are now very interested to listen to your presentation. Luc.
Thank you, Christoph. Okay. So now I will share my screen. You see it?
Yes, perfect.
Yes.
Okay, thank you. Okay, I'm very glad to join the Vector Forum. And today I will be talking about autonomous driving systems for mobile robots and vehicles. In this presentation, I'll briefly introduce the application and developments of mobile robots and discuss the key technologies used in robot navigation, including the localization algorithms, path planning algorithms, and the perception algorithms. And I will also introduce the software middleware for mobile robots, the Robot Operating System, ROS. And in the end, I will give you a simple example of a mobile robot to demonstrate how these technologies can be combined to enable autonomous navigation. So in the first part of this presentation, I will introduce the applications and developments of mobile robots. And with the advances of robot technologies, there are various applications of mobile robot in different fields. One example is the AGVs used in industrial environments. In the video on the left, we can see how these small robots move cargoes from one place to the other in a warehouse. Another example is the application in agriculture. Due to shortage of the labor force in agriculture, mobile robots can be helped with the tasks like logistics and pest control. And mobile robots are also widely used in service industry, and you can see almost you can see robots in almost every hotel in China. And from the video, we can see a small robot. It helps the hotel staff quickly deliver items to guests, and that saves a lot of time and reduces the safety risks. So with growing demand for the mobile robots in different scenarios, the market for mobile robot is also expanding rapidly. According to statistics, about 102,000 mobile robots were sold in China in 2023. The number increased by 26% compared to 2022. And the predictions suggest that this number will reach 128,000 in 2024. Additionally, the mobile robot market is also highly concentrated. The top 5 manufacturers occupied about 50% of market share in China. And there are two main types of mobile robots, AGVs and AMRs. AGV is the abbreviation of automated guided vehicle. They usually travel along fixed paths or tracks, and they are guided by tags in the infrastructure. And such as magnetic tracks or wires. In well-prepared scenarios, AGV systems are simple and reliable, but they cannot handle dynamic obstacles. They will stop until obstacles are removed. And AMRs stand for Autonomous Mobile Robots. They can navigate autonomously without support from infrastructures. AMRs are more flexible and intelligent than AGVs because they can detect obstacles in the environment and safely maneuver around obstacles. So AMRs are becoming the main trend of mobile robots. So we can see that autonomous navigation is the core technology of mobile robots, and it consists of several modules. First, we collect data from sensors in order to perceive the external environment. Then, based on the sensor data, we locate a robot and help the robot understand its current position. Next, we need a path-plan algorithm to calculate the best route from the current position to destination. Based on the robot's kinematic characteristics, we calculate real-time motion commands for the robot. And finally, we will send these control commands to the actuators. And this diagram shows the data flow of the navigation system. So the next part is about robot localization algorithms. Localization algorithms solve the problem of where the robot is. In autonomous driving systems, localization results should be highly accurate with low latency. And it also needs to be robust enough to reduce external interference. And the video on right shows a localization experiment we carried out in our campus. We mounted the GNSS and IMU sensors on a test vehicle and use an extended Kalman filter to calculate the position of the vehicle. The orange circle stands for the test vehicle. And the one interesting thing of this test is that when the vehicle enters the garage, and in normal case, the error accumulates because the loss of GNSS signal. But we can see in this case, the result is still very reliable. And in order to collect the environmental data, we use various sensors. Commonly used sensors include camera, LiDAR, IMU, radar, and GNSS. And in this slide, I list the advantage and disadvantage of all these sensors. Cameras can provide image with rich texture information, and the price is also affordable. But the image data processing is always very challenging. So we need various techniques like computer vision and neural networks. LiDAR can provide accurate measurement of the distance to the objects and offer the point cloud of the surrounding environment. But the price is the biggest disadvantage. And LiDAR could also be sensitive to bad weather conditions. IMU is an inertial measurement unit, and it provides information about the vehicles in movement. IMUs based on MEMS technology are usually very cheap. But the main problem is the drift error, and that error will accumulate with time. Millimeter wave radar is widely used in vehicles. They have long detection range and very good robustness. But the resolution of radar is usually very low, and the results are normally affected by multipass effects. GNSS has a very good coverage and can provide global localization results. With the help of RTK technology, GNSS can usually achieve very high accuracy, but GNSS highly rely on the signal from satellites and usually cannot function properly when signal is blocked by buildings. And for localization, there are normally two types of methods. One is a multi-sensor fusion method based on filters, and another one is SLAM. For the filter-based method, Bayes filter like Kalman filter is used to integrate the information from sensors like GNSS and IMU to get accurate and reliable localization results. So in the diagram, we can see that the signal from IMU and the GNSS are integrated to get the final result. This method can work properly in outdoor environments as a satellite signal can be well received. So it is widely used in outdoor agriculture robots. It also requires very low computation power, but it is highly reliant on the GNSS signal, so it cannot function normally in indoor environments. Another method is called the simultaneous localization and mapping, or SLAM. From the name, we know that this method establishes an environmental map during localization. And when the map is created, by comparing the sensor information with the map, we can get the location of a robot in the map. And this diagram shows the structure of a typical vision SLAM system. Normally, image data and the LiDAR point cloud can be used to create maps. In SLAM technology, we need to extract a feature from sensor inputs and save them in the map, and then perform a feature matching when necessary. And the red and the green dots in the video stands for the feature we extracted from the image. The advantage of this method is that it does not rely on GNSS signals, but its performance is affected by the accuracy of feature extraction and the versions of the map. And with the development of deep learning technology, end-to-end localization method also becomes a new trend. Compared to the traditional method, this method doesn't need carefully selected features. It directly feeds sensor inputs into a deep learning network and extract the feature with the network, then output localization results. This method has a great potential, but the generalization of the model is the biggest challenge. And after we get the robot's position, we need to find the feasible path in the environment to ensure that the robot can reach its destination efficiently and safely. And this is the task of path planning. And normally, robot path planning is a two-step approach. The first step is the global path planning. In global path planning, we look for a complete path from the start point to the destination in the environment. So it means that we need to use a map or model to represent the entire area. And in stable and well-known environments, global path planning can work stably. And the second step is called local path planning. After we get a feasible path from global path planning, we extract local planning targets from the local global path points. We also need to detect the dynamic objects in the environment based on real-time sensor inputs, and then generate the safe avoidance paths. In local path planning, we will also have to consider the robot's the dynamic characteristics and calculate the movement in real time. And in this slide, we can see several commonly used algorithms in global path planning. Dijkstra's is the most classic algorithm in path planning. It is based on a graph search method to find the shortest path from starting point to the destination. Dijkstra uses a depth-first search method, which ensures that it can always find the feasible path, but also increase the computation load. And the A-star algorithm is an extension of Dijkstra algorithm. The A-star algorithm uses a heuristic function to estimate the possible cost from the current position to the target. It allows A-star algorithm to plan paths that can avoid obstacles with less computation load. And the RRT algorithm is a sampling-based algorithm. It builds a growing tree from the starting point towards the destination and explores feasible paths in the space. And it performs well in complex environments. The bidirectional RRT is an extension of RRT. It simultaneously builds two trees that grow toward each other from the starting point and the destination. So bidirectional RRT can explore the environment from both directions and improve the efficiency of path planning. And there are also different algorithms in local path planning. TEB is an optimization-based path planning algorithm. It takes global trajectory, obstacles, time constraints, kinematic constraints as part of the optimization loss function and finds the best paths through an optimization process. And DWA, dynamic window approach, is a sampling-based method. It samples various velocity in the space and verifies whether paths may collide with an obstacle. And it can very effectively calculate a safe driving path. In the APF, artificial potential field method, the target is represented as an attractive force, and the obstacles are represented as a repulsive force. And by combining these both forces, we get the movement direction of the robots. And MPC is a control-based method. It predicts the behavior of a system over a prediction horizon and takes the dynamics of the robot into account. It selects the optimal control strategy based on optimization results. End-to-end methods are also used in path planning. They take sensor information as input and generate the robot's control command directly. In addition to traditional CANs, transformer and diffusion policies are also applied in end-to-end path planning algorithms, and that improves the performance significantly. Another important part is the robot in the robot navigation system is the environmental perception algorithm. Perception algorithm helps a robot understand the surrounding environment and choose the appropriate path. According to the sensors used in perception algorithms, they can be categorized into image-based approach, point cloud-based approach, and multimodal approach. For the image-based perception, deep learning algorithms based on CNNs are widely used, such as the fast RCN and the YOLO. The fast RCN is a two-stage deep learning algorithm. First, it generates candidate regions for object detection by separating background from foreground, and then identifies the targets in these areas. In that case, the fast RCN algorithm has better detection accuracy, but it is also slower than the one-stage algorithm. And the YOLO is the abbreviation of You Only Look Once, and it is a one-stage method. It directly generates the bounding box and the classification results. So YOLO is faster than fast RCN, but the detection accuracy is lower, especially for small objects. An image-based perception algorithm, the transformer is also widely used. For example, the DETR. DETR uses a convolutional neural network to extract the image features, then converts the features into tokens, and use the encoder-decoder structure of transformer to generate detection results. And thanks to the self-tension algorithm, self-tension mechanism, DETR can consider the whole picture at once and identify global conditions in the image. So DETR tends to have better performance in object detection. And lighter point clouds can provide the spatial geometric information of objects. Similar to image-based perception algorithms, deep learning algorithms are also used to extract features and detect objects in the point cloud. PointNet, VoxelNet, and point pillar are the most famous point cloud detection algorithms. PointNet uses MLP to extract features from point clouds directly, and use a T-network to estimate the transformation of point clouds, and it can be used for various tasks, such as object detection and segmentation. And in VoxelNet and point pillar, the point cloud is firstly converted into voxels and pillars, and then the features are extracted. So in that case, it reduces the computation load and improves the detection performance. And robots are usually equipped with more than one sensor, so the accuracy of detection results can be effectively improved if the information from these sensors can be fused. Sensor fusion algorithms can be categorized as post-fusion and pre-fusion. In post-fusion algorithms, it integrates the detection results from different detection algorithms to get more robust and accurate results. Pre-fusion is the fusion of raw sensor data. By using multimodal networks, this method can effectively improve the detection performance. And in addition to navigation algorithms, the software middleware is also an important part. The most widely used software middleware in mobile robot is ROS. ROS is an open source software framework for robot software development. It provides powerful tools and the library functions for the software of the mobile robot. Its core component is a flexible communication system. In the ROS communication system, topics are used for passing asynchronous messaging, and services are used for synchronous remote procedure calls, and actions are used for handling preemptible tasks with feedback. And in the example on the right side, we can see that this is a distributed communication system. Laptop and robot computer can exchange data through ROS. And for the application software, it only has to subscribe to the interest topics without considering where it comes from or on which platform the specific components are running. And ROS also provides tools for robot software development, such as RQT and AVIS. And RQT is a Qt-based framework, and that provides a flexible and powerful user interface, including various types of development tools and graphical plugins. And that help us to interact with the robot's operating system visually. And AVIS is a 3D visualization tool that allows users to visualize sensor data and the robot architecture in 3 dimensions. They are all very helpful for debugging and developing complex robot tool systems. And the ROS2 improved the reliability and real-time performance of ROS1. ROS1 is more concerned about the simplicity of the system, and it provides a large number of robot development tools. ROS2 has enhanced the system's security, real-time processing performance, and the multi-platform distributed architecture. It also provides many new features, including multi-robot transformation, small embedded platform support, and minimize the ROS data transmission impact from network quality. And finally, I will show you a simple example of a robot navigation system. We built this mobile robot 2 years ago. The appearance of the robot is designed according to the vector car. It is equipped with a 32-line LiDAR, wheel speed sensor, and 6x IMU. And based on these sensors, it can perceive the environment, detect obstacles, and get the position of the robot. And for localization, we use a LiDAR-based STAM algorithm, which is very effective in indoor environments. And for path planning, we use A* as a global path plan algorithm and TV as the local path plan algorithm. And the entire software system is based on ROS, and the control hardware is based on Infineon Oryx and NVIDIA Xavier modular. And in this slide, we can see the test of the autonomous navigation system. And from video, we can see that the robot can detect dynamic obstacles and maneuver over the obstacles. And in the end, it's a very short summary, and it could be some question you should consider before you want to build your own robot. Firstly, you have to consider what is your environment. Whether it is indoor or outdoor, and then you should decide which sensors are you going to use. Because IMU is always very cheap, and you can deploy it in your system. So I think you should choose IMU. And if you are used in outdoor environment, I think GNSS might be necessary. And the cameras are very cheap, but the image processing for cameras is very difficult. So maybe not the best choice for the beginners. LiDAR can provide very accurate measurement of the environment. So we can, if the budget allows, you should use LiDAR. And then you should consider which localization algorithms are you going to use. Whether if you have the GNSS on board, maybe you should use the field-based algorithm. And if you have camera or LiDAR, maybe you can use them. And then which pass-plan algorithm are you going to use? And at this time, you should consider your computation load, because some of the pass-plan algorithms need a very intensive computation power. And also, you have to consider the complexity of the environment. And then you should choose your perception algorithm. And it highly depends on your sensor setup. If you have camera, you should use the image-based perception. If you have LiDAR, you should use the cloud point. And if you have both, maybe you should try sensor fusion algorithms. And then is the middleware, whether are you going to use a ROS1 or your ROS2. And ROS1 is majorly focused on the simplicity, so it is quite suitable for beginners. And ROS2 focuses on the efficiency and security. And if you want to build a secure robot, maybe you should use ROS2. Welcome to the Vector Forum, and thank you for your attention. Looking forward to your questions. Thank you.
Thanks, Luke. Excellent presentation. Very much appreciate this. It was almost a full tutorial on how to develop such robot system, what ways to consider with the different, let's say, system basics, such as the platform, the sensors, the planning, the usage of different sensors and sensor fusion. Very good. Thank you very much.
Thank you. Thank you.
Let me just go then to the result of the survey. You might be interested to see where we ended up with. So we had about 7 who say yes. We had 93 which say no. And on that basis, I would now proceed to the questions, because I think that is what is now most interesting. And I see in the chat already some questions. Yeah, there are quite a lot of questions appearing. There's no vote yet, so let's start with the first one, which I think is market-related questions, always a good starter. Do you see a growth rate similar to the 20% that you mentioned for Chinese market globally, or can we see that in some regions the speed is higher than in other regions? Can you just give us a few insights about how you foresee the global average growth rate for robots?
Okay, that's a good question. But I didn't do a survey over the global market of a mobile robot, but I'm quite sure that the situation might be the same as in China.
Okay, so you can imagine that different regions have different speed, but would be a similar, let's say, pattern. Okay, then there come question. What experience can you share on developing autonomous systems? So I think that is a rather broad question, and you can imagine this can be filling hours. You gave a nice example at the end with some questions what to consider when building a robot system.
Yes.
But maybe beyond that, just from your own experiences, what would be interesting takeaway? Just to give you one idea, which I had when I was watching, I mean, robots are autonomous. Maybe you would also talk about connectivity and the loss of connectivity, reliability, the functional safety. I mean, there are many such topics, but go ahead.
Okay, that's a really very big question. And I like to say that, well, today's topic is about the autonomous driving system, and that is not just for a robot, but also for the vehicles. And we all know that autonomous driving vehicles is a very hot topic at this time. But I think the biggest challenge is the safety of the system, and how to verify that the system is safe enough, and how to test all these algorithms, especially when there are AI embedded, the algorithm based on AI and neural networks. And currently, we know that all these algorithms they are black box, and it is very difficult for us to understand how the network learn and how it works. So I think that might be the biggest challenge for the autonomous driving systems. And also for the other aspects, for example, I just mentioned that we developed the controller for the robot by our own. And it is quite similar to the autonomous domain, autonomous control unit for vehicles. And you should consider which sensors and which kind of interface you need, and the connectivity, the information exchange from the domain controller to other units on the vehicle. Yeah, I think that is a very broad question and a very big question.
Yes, and then we can certainly take more examples, because we see autonomous systems all over. We see them in the industry plant, we see them with vehicles, we see them increasingly in medical surgeries, we see them in space stations, and of course each one has their own specific environmental constraints.
Yes.
Another one would be about the testing. What testing methods do you deploy for ensuring that autonomous systems actually perform as expected? In other words, maybe you can just give us an overview. I mentioned in the introduction already, for instance, the safety of intended functionality. In other words, there are new patterns coming along, but what is your experience here to make effective testing?
Okay. Yeah, I think the testing for robots and for the vehicles are quite different. And for the robots, well, as I mentioned, we use ROS, and ROS provides a lot of tools. We are be able to simulate. We are be able to build the simulation environment in ROS and verify our software by ROS firstly, and then deploy the software into hardware. And then we can do a hardware in-loop test, and in the end we can verify the robot in a real environment. And for vehicle test, I think the process might be the same, but the requirement I think is much higher than the robots. And for example, for the perception algorithms, how to verify that, how to make sure that your deep learning neural network works properly in all cases, especially for the edge cases. That is a very big challenge. I think that is the reason why mobile robots they come to real application very quickly, because most of the robots move slowly, and the safety requirements for these robots might not be that high as vehicles.
And related to that, since we work in the same domain, can you give examples of what would be appropriate test end criteria? In other words, you can always test, of course, infinite amount of scenarios. We know that from autonomous driving, where cars would collect data with loggers and different sensors for hundreds of millions of kilometers, but still some situations just don't happen, and therefore you can never really be sure that you have tested sufficiently.
Okay, yeah, I think that maybe a short answer to that question is it's very difficult for you to make sure you have tested sufficiently, and yeah, it is very expensive to collect the real data with the real vehicle and the real sensor in a real environment, and you have different weather conditions, so you have different road conditions, and with the daylight and all these things, it is very difficult. And I think nowadays there are some new technologies like the simulation with, for example, the nerve, some other technology that people try to generate simulation data, which that is so real that you cannot tell difference between the simulation data or the real data. And I think this kind of technology can be used in autonomous vehicle testing to maybe that can help us to find the corner case or the flaws in the software. But I think that is a question related to the SOTIF, the safety of intended safety and intended functionality. And I think that is an open question, and it is very difficult to say that you have tested sufficiently.
Mm-hmm. One question which is related to the functional safety is what kind of approaches do you implement? So we're not talking about testing, but more the implementation, the development, the design strategy, such as fail operational measures. What kind of approaches do you take to make these robots safe, but at the same time also still performing, because you cannot always just wait for new commands?
Okay, that's a very good question. Actually, for this small robot, because it moves so slowly, I think that if we do the hazards analysis, maybe it's QM. I think maybe it's a QM. So and actually, we consider the safety of the robot in our hardware design. So we use the Oryx Infinite, the Oryx Brain Infinite with the NVIDIA Jetson Xavier module, and the application software, most of the application software is running on the NVIDIA module, but we have Oryx as a monitor of the module of the NVIDIA module. And we will continuously monitoring the operation of the Jetson module. And in case there's something wrong, and because we define some protocol like the heartbeat signal or CLC check or something else to make sure we can monitoring the operation of the module. And in case there's something goes wrong, and we can switch off the power supply of the robot. So I think this is one safety consideration in the robot design. But as I mentioned, that because the robot moves so slow, I think it's a QM product. So maybe in an emergency case, maybe we just have to stop the robot.
That's true, but I recall this is exactly one of the challenge in one of these pilots in San Francisco, that the cars, you remember, there's for instance Waymo cars running autonomously in the city. They slow down very much in order to be safe. But now the city council says, well, this could in emergency situations like an earthquake be rather critical if they just block roads or corners of roads, because then the fire brigades could not anymore really pass through. So you need, let's say, fail operational strategies which also consider emergency situation.
Yes, you are right. Yeah, for autonomous driving vehicles, the situation is different. Normally, we will for different level autonomous driving vehicles, we have different requirements. And in case a vehicle with level 3 or above, we need to. I think the system have to be operational, be operational, because for the L1 and L2, we always have the driver in loop, and they can monitoring the system. And in case something goes wrong, and we can have the driver to jump in to stop the vehicle. But for the vehicle with level higher than level 3, then we allow the driver to distract from driving. So in that case, we have to make sure even something is going wrong with the system, we have to make sure it can operate somehow. For example, it can pull over, stop by the roadside, or do something in the emergent situation, not just a stop.
Yeah. Right. Now, a question of Mr. Wenbo Tong. He's asking what kind of regulations are around for security and safety of such robot systems. Can you just mention one or two which are really the important ones?
I think for the safety of the robots, because it's an industrial product, we should follow the ISO. I can understand I cannot remember the number of the standard, but I think there are some security and safety requirements for industrial products. And if it is a vehicle, you have to follow the ISO 26262.
Yeah. But it's also like the normal machinery standards like the 25119, etc.
Yes.
Okay. And there's a question from Mr. Raj Kumar. He wants to see how to validate quickly the quality of the data that is used. In other words, I mean, you have a lot of data. We also know in the meantime that from autonomous vehicles, they can be easily faked. I mean, the human would still see because of the the context awareness, but the robot might not anymore see that the data is wrong. If it's, for instance, a visual data where you change a number sign with a speed limit, it takes only a few marks to make a 30 to an 80, which can be very difficult and dangerous.
Mm-hmm. Yes, I think that is a question related to the security, because this is some intended attack. Some intended attack to the autonomous driving system, and I think that really a question for the deep learning algorithm, because we don't understand how it works, and we do not know which kind of feature extracted from the image and from the sensors. And I've also read some papers that someone working on this topic that maybe we can have some special training process to make sure that the system is more robust to this kind of attacks.
Mm-hmm. Yeah, indeed. I mean, this is always this balance of robustness and imagining specific corner cases. I have one last question because time is running from Mr. Stefan Walter, and he's asking more an experience question. Based on your experience, what time to market would you assume for a simple indoor delivery robot, from I perceive, from the inception to the go-to market of such a system? What time is necessary to do that?
Okay, yeah, and from the slides, there's an example that I mentioned that the small indoor delivery robots in the hotel, and we can see the robots almost in every hotel in China, and it is very common here. So I think maybe now is the best time to put that product into the market.
Yeah, and experience shows, given that there's so much platforms available like the ROS2, which you mentioned, the real development which comes on top to connect your sensors for a specific application and performance, that should be done in the course of a few months. And then, of course, you have the production and deployment. But time is short, and we talk for less than a year. Okay. Thanks again, Luke, for this really good and insightful presentation. Very glad that you shared your experiences. And
thank you.
I will now finalize with a few further slides, also give you an outlook on where we go from here. And the outlook would be that we have now each Wednesday to come, still a few more such presentations. Next week, as I said, was software architecture and for medical devices. And that means we will further look into all sort of emerging technologies. And the five experiences which we want to share on the left side really nicely connect what we also had in this excellent presentation of Dr. Luque from Tongji University. Namely, we talked about needs in terms of market, understanding the market, but then also needs in terms of the technology and the functionality. Make sure you focus in order to deliver. We learned about single sensor, multi-sensor, different learning, different positioning algorithms. We had also these interesting questions about time to market. The quality must be certainly good enough, but with all learning systems, we can never be complete. So we have also to build some protective or robustness mechanism for cybersecurity and for autonomous safety. And I think also what we could see in the learning algorithms, in the sensors, is that we typically grow incrementally. We should not shoot for the very most complex system, but rather learn and grow. And in doing so, evolve competencies and then go for the next step. Next step also in our Vector Forum, we look already ahead for 25. You can register as of now. There's a QR code on the page. It will be similar mode than this year. And what we want to focus next year is how to bridge ecosystems. We see already now that we have more and more convergence of IT, operational technology, OT, and the Internet of Things or embedded electronics. This is further growing. We see that obviously with the robots and autonomous systems, which are typically always connected to some sort of backbone. But here questions could come around. How do we actually structure such software-defined systems? What would be the learnings from this convergence? And of course, again, also how do we connect agile development with safety, with reliability? And not the least, because we often forget about that, it has also to do with the organization and the evolution of organizations. So go ahead, can register already now and you get all the information. And don't forget our quiz I just mentioned before. And the link would be on our homepage, which is www.vector.com. And then you go to the consulting and find also this quiz on Vector Forum. And that being said, and also looking to the clock, we have reached the full hour for the Europeans a lunch break. In Asia, it's more kind of an afternoon coffee or tea, and in the United States, just the breakfast entertainment. I'm very glad that you all joined today for this very insightful presentation of Dr. Luque of Tongji University, Shanghai, on autonomous systems and how to really build those systems in terms of sensors, positioning, algorithms, learning, and not the least also real hands-on practical guidance. And I look forward to further connect with you. Thank you and good success with building your own automation and autonomous systems.